Welcome to this explainer. Today, we're going to unpack the secret code that allows computers to understand human language, step by step. If you've ever typed a message, sent an email, or literally just read text on a screen, you've relied on an invisible translation process that is constantly running in the background. So we are going to make that invisible process visible.
So, here's the central problem we've got to tackle. At a hardware level, computers only process binary electrical signals, right? Just endless patterns of ones and zeros. How in the world do we get from a raw electrical pulse to a fully formatted text document complete with global symbols and smiley face emojis?
Here's our roadmap for today. We'll start off with the language barrier, look at the ASCII character set, explore going global with Unicode, break down encoding step by step, and finish up with the storage trade-off. Let's dive in.
Section 1. The language barrier, bridging the gap between human and machine.
To actually bridge that gap, we need a translator. And in computer science, that translator is called a character set. Think of a character set like a massive lookup table. By definition, it's the collection of all characters and symbols that can be represented by a computer system. The real magic here is that every single letter, digit, or symbol in this set gets assigned its very own unique numeric value. When you press a key on your keyboard, your computer doesn't actually see a letter. Instead, it checks this table, finds the unique binary value for that specific key, and just processes the math.
Moving to Section 2, the ASCII character set, the first decoder ring.
So ASCII, which stands for American Standard Code for Information Interchange, is essentially our baseline. It assigns a specific denary or decimal number and a corresponding binary number to every single letter. Take the capital letter A, for example. In the ASCII character set, A is assigned the denary value of 65. In binary, that translates to 100,001. Capital B is 66, C is 67, and it just keeps going. It totally proves that, to a computer, the alphabet is literally just math in disguise.
Now, here's the catch. While ASCII was completely revolutionary at the time, it's actually incredibly limited. It's a 7-bit set of codes, which means it only has the capacity to hold 128 different characters. And 128 characters is really just enough to cover every uppercase letter, lowercase letter, digit, and basic punctuation mark on a standard English keyboard. Because of this strict cap, ASCII is pretty much exclusively used for the English language.
But there is this absolutely fascinating mathematical quirk built right into the system to handle uppercase and lowercase letters, and it all revolves around the number 32. Remember how we said capital A is 65? Well, if you add exactly 32 to that, you get 97, which just so happens to be the ASCII code for lowercase a. And this trick works for the entire alphabet. In binary terms, capital letters always have their 32-bit turned off. It is a brilliantly structured, super elegant way to organize language using pure math.
All right, Section 3. Going global with Unicode, breaking the 128 character limit. Because let's face it, 128 characters is nowhere near enough for a connected world. Now, there was an intermediate step called extended ASCII, which used an 8-bit system to give us 256 characters. That was helpful for European symbols, like an E with an accent, but just think about the staggering difference in scale required for modern computing. On one hand, you've got this tiny sliver representing the 128 characters of ASCII, but on the other hand, you have Unicode, which just bursts open to over 1.1 million potential characters. Unicode was built to accommodate practically all global languages, symbols, and even emojis, all in one unified system.
When you put them head to head, the evolution is pretty wild. ASCII is this simple 7-bit system, capped at 128 characters and restricted to English. Unicode, though, it's an absolute powerhouse. It uses anywhere between 8 and 32 bits per character. And by using up to 32 bits, Unicode can actually represent up to 4 billion unique characters. This means that every single language on Earth can have its own dedicated block of unique binary codes.
The real-world impact of this is massive. Think about it. Global platforms like Facebook or Google simply couldn't function using the old ASCII set. Why? Because their users are communicating in hundreds of different languages simultaneously. Unicode is the invisible framework that actually allows people on the exact same platform to chat in Mandarin, post in Arabic, and drop emojis all at once without the computer ever getting confused.
Which brings us to Section 4, Encoding Step by Step, translating the word Patel. So how does this actually happen in real time? Well, the mechanics of encoding are super logical.
and strictly sequential. Step 1. The computer recognizes that each individual character in a word has its own unique binary code in the character set. Step 2. It breaks the word apart and replaces each character with that specific binary value. And Step 3. These binary codes are stored exactly in the order they appear in the word. So, for the name Patel, the machine first replaces P with its code, then A, then T, then E, and finally L, writing those binary values sequentially, right into its memory.
Finally, Section 5, the storage trade-off. More characters, more problems?
You know, there's always a catch in computing, right? There is a direct trade-off between capability and resources. The huge advantage of Unicode is obviously that it can represent 4 billion potential characters globally. But the disadvantage? Because Unicode needs to use up to 32 bits for a single character to give us those billions of combinations, compared to ASCII's tiny 7 bits, it inherently requires more memory. If you save a massive text document using Unicode, it is going to take up significantly more storage space on your hard drive than if you just saved it in basic ASCII. More combinations simply demand more digital real estate.
So it really leaves you wondering, right now, as you're reading the text on this screen, how many invisible bits of data are being processed? From simple 7-bit letters to massive 32-bit global symbols, there's an incredibly complex, lightning-fast translation happening right under your fingertips every single time you tap a key. It's pretty amazing, isn't it?